Okay, the next theorem we're going to look at is the mean value theorem. Mean to you should mean average. So this is basically the average rate of change. It is a very specific case of the, well, actually Rolls is a very specific case of the mean value theorem. So the first thing we're going to do is look at what does it mean. So I'm going to write it down real quick, and then you just copy it down. Yeah, I'll go ahead and write it down. What the heck? So let's see. All right, so here's what the mean value theorem is, and you can go ahead and pause it and you want to write it down real quick. It says, let f of x be continuous and differentiable on a closed interval a, b. There exists a value c such that the derivative at c, so the slope at c, is equal to the average rate of change, or the slope of the secant between 2 points. So now we're trying to make a connection between average rate of change and instantaneous rate of change. We've already used it once to approximate what we thought the slopes at 4 and 6 on that first function were, and we've used it in the past doing the exact same thing. So now that's what we're going to be doing with this, is making connections, using it when we need to approximate slopes, and then proving that a certain slope would have to exist because this theorem says it must. At some point there is a slope that's identical to the average rate of change. Okay, this function says the graph of h of x is pictured below. Does the MVT, which is the mean value theorem, apply on the interval from -1 to 5? And this one is going to be difficult if you really aren't sure what the graph is here, -1 to 5, but there is a vertical asymptote right here at x equals 0. It's undefined. And since x equals 0 falls inside of this closed interval, then no, I can't use no, because h of x is not continuous. So always check that you are continuous. Always to check to see if it's a function that has a derivative that's defined. So if you do the derivative of this and you still get values that aren't defined, then you can't use this theorem as well. Okay, the next part says, does the MVT apply on the interval from 1 to 5? So if we change our domain from 1 to 5, am I allowed to use the mean value theorem? And go ahead and figure out what you think it is. All right, so the answer is yes, because the function is continuous as I go from 1 to 5. It is differentiable. I don't see any cusps in there as I go from 1 to 5. And so I'm allowed to use it. So that would be your explanation, one of the two things I said. It's continuous and differentiable. It says graphically, what does the MVT guarantee for the function on the interval? Graphically. So graphically, what it says is the slope of the secant. So from that coordinate point to that coordinate point, the slope of the secant. There is another slope on the curve representing the instantaneous slope that will be equal to it or parallel to it. Somewhere else it will be parallel. Okay, so what it says is that f prime at some value will equal the slope between x equals 1 and x equals 5. You're guaranteed that. And so it's going to be a parallel slope. Because slopes are the same. And so now now you know. Now you know for sure if you're looking for a very particular slope, or if you want to show that the graph is increasing but all you know are 2 coordinate points, you use Rolle's theorem, or in this case the mean value theorem, and you've basically proven that. Okay, so since we have shown that there is a C value that will have the same slope as the secant line, then we should be able to find that C value, very much like we did with the Rolles. So it says find the values of C to guarantee, find the value or values of C guaranteed by the mean value theorem on that closed interval. So that means, once again, we need to do the derivative of our function. And you can go back up and look at the function. And it says h of x is equal to 3 minus 5 over x. And that means my derivative will be 5 over x squared. Okay, so what the mean value theorem says now is there exists a C value that when I take its slope at C, it is equal to the average rate of change between 1 and 5. So f of 5 minus f of 1, 5 minus 1. Over here I'm going to do the derivative but plug in a C, so it looks like that. Here I find these different values, so f of 5 is 2, f at 1 is negative 2, and that's 4 over 4, which is 1. And then just do some quick algebra, and I get 2 answers, plus or minus the square root of 5. All right, now only one of these we are allowed to use. Think about it for a moment. Why are we only... Okay, we're not allowed to use the negative square root of 5 because it doesn't fall in the closed interval 1 to 5. So the only C value that works is the square root of 5.